I was watching some video, some black and white security video, and I saw these out of focus dust particles that people call ghost orbs. But it's dust floating around and the light's reflecting off of it in a certain way, and it's all blurry and kind of soft, and they're moving with the air. If there's any draft that's going back and forth, you can kind of see this movement in the collective motion of all these particles. So I thought, okay, I've made some particle systems in the past that move around. I made some fireflies. There's a link to that episode right here. So it's kind of sort of the same thing, these things flying around, but I want their appearance to be ghost orby and not firefly-y. So that's what we're going to do in this video. Here's the ghost orbs here. I call them ghost orbs. It's just easier than blurry dust particles because I think most people realize what a ghost orb is. Now there may be real ghost orbs. I'm not here to debate that. But I can tell you from my experience and the observations that I've made, the overwhelming evidence is that most of the ghost orbs we see are dust particles. Now maybe there's a ghost orb, a real life ghost orb in there somewhere, blending in with the rest of the dust particles, but they're dust. Here we have the dust moving around and it's kind of floating upward, it's dropping down, they're swaying back and forth, and they're doing it in a kind of an organic way. It's not Brownian motion. It's Perlin noise moving in kind of a wave form. They have different sizes, and every once in a while if you look, you'll see that the intensity, they'll flash, they'll flicker. I call this glint. As the particle is spinning, facets of it will reflect the light more intensely, and because it's outside of the focal plane, this intensity gets magnified but blurred, and you can see it in the overall intensity or appearance of the particle. So it kind of brightens up and then dims back down as it spins, and it may do this cyclically or randomly depending on how the air is moving this irregular particle around. If you look at dust really closely, you'll notice that most of it is strand-like, especially the dust that floats in the air like these particles. They're like strands or fibers. So they have this irregularity in their shape, and they're almost sail-like, that they'll spin and cup the air and do all kinds of weird optical things that you can see clearly in the appearance and the brightness of it. So I wanted to capture that. Here's the program that we're going to write today without the annotations. I've got my notes in there so I can remember what's going on. It's not very long. It's pretty easy to put together, and I guess the best thing to do is to just start a new sketch. We'll use the available window width and window height. Let's set the background to a dark gray and give ourselves some room to work. In our global space, at the very beginning of our program, we want to assign some global variables. We need one to hold our particle system. So we have a number of particles in the system, and we're going to use an array to hold each of those particles. I call the particles orbs, and a single orb in an array is called an orb. So to remember, if I wanted to call the particle system orbs, because it makes orbs, and then each one of the elements in the array would be an orb or singular, that'd be one way that you can remember whether or not it's got an S on the end or not. Which one of these am I working with? Am I working with the single element in the array? If it is, it's singular. If I'm working with the function or the class, then it's plural. How many orbs are there in my system? Let's have 40, sounds like a good number. That's all of our global variables. Then inside our setup, we're going to create a loop that goes through all the elements and assigns a new instance for each particle. So we want to do our for loop. We're going to use I as a variable in this loop because whenever we're dealing with a variable that handles the elements of an array, that's the index value, and we use I as like the shorthand for index value. And if you maintain that standard, it kind of helps you read your code and manage your code later on. What variables am I working with? Which ones do these stand for? And you always know to go to that one. You never have to be like, which variable do I want to use for this loop? You just automatically know. This isn't a loop through an array, I'm using the I. And then if you see an I, you know, like that's the index value. We're going to loop through that array the number of times of particles that we have, and we're going to increment one integer each frame, and that's going to give us an index value, an integer index value. p5.js is going to go through the loop. It's going to look at this variable right here, and it's going to see the dot syntax, and then it knows that it's going to be doing something with this element. If you put dot push, it knows I'm going to be adding something to this element of the array. If you type new, that tells p5.js that you want to create a new function or a new class. So when p5.js goes to this function or this class for the first time, it's going to go through the global space of that function and the instantiation space, I call it. That may not be the exact word, but that's kind of what I call it, because that's what's happening. When you instantiate, you're calling those variables that's in that main function space. And then there's methods also that are in that main function space. But those methods are kind of excluded unless they're called independently. So you have kind of like one section of the function that gets run initially when you use this new keyword, and then the methods can be isolated and run separately whenever you need to use those. So we're using the new keyword, and we're calling the particle, the object. This function is going to go into this element, and that element is this variable. May sound kind of complicated. I probably didn't explain it the best way. I've explained it before, but in a different way. So I just kind of like explaining things in different ways, and maybe that'll help crystallize the idea with people who just didn't understand it the other way. Once you've created the loop and you've instantiated these particles, we can start doing something with them. We have this array of particles now. We can do whatever we want with them. Well, almost whatever we want. The first thing we need to do in draw is loop through those particles and do something. Just as a matter of practice, if I'm looping through an array inside draw, I want to use the orb, or use the variable name .length, and it will return the length of that array. If I should happen to change this variable here, and then for whatever reason I don't use it here, well, then everything else down the line is going to fail. So one of the ways that you can always make sure you've got the right number to use for the array length is just use this. This is the reason why it was included as a method for arrays, is to solve that problem in case you change something you don't realize it. This way it's always going to be attached to an actual or real value instead of a variable representation. We're going to increment through that loop, one integer per frame, and then inside the loop we have to call the individual, we have to use the individual element. So right here inside brackets, I'm going to put that index number, and that's going to tell us which object particle we're working with. Then we can start doing stuff. Whatever methods are inside the function, we can call those now for that particle, and it's just going to operate on that single particle. Then we can move to the next particle, do its update that handles all of its unique characteristics, and so on and so forth, so that each particle in the system is treated as kind of a separate thing. We're going to call update, which is going to do the moving, it's going to do the glinting, and it's going to do a bounds check, and it's going to display the output. Since that update is doing everything, that's all we need for draw. Everything else is going to be done within the function, and this is kind of how you want to code, because if you're going to transport these functions into other programs, which is likely, the less attached they are to draw, the easier they are to port. So you want to put as much stuff in the function as you possibly can, so it's easier to carry over. So if I want to port this, all I have to do is carry over the function. That's it. And then if I want to use it, then I can use it in whatever way. Assign, maybe I don't want it to be orbs, maybe I want it to be fireflies. Change that. But I don't have to change the function. As long as I'm assigning the function name particles to whatever variable I'm using, it will use that. It'll know what's going on. We're ready to create the function particle. Let's give ourselves some space. I named it particles. New particles. I'm going to call it particles because the function is creating particles. I want it to be plural. And then if I could have put particle here, put particle as the array name. Just do that. So wherever I used orb, I have to change it to particle if I want this to work. So now I've changed this orb name to particle, and a particle is one of many particles, which is the name of the function. Does that make sense now? Did that make sense before? Will it ever make sense? Inside our particles, remember I was telling you about whenever we create a new instance of a particle, we're going to use this global space here. It's not the global for the program. It's an instantiation space. So as an object, when I create this object for the first time, I want it to have a position, and I want that position to be a vector. The vector is going to have a random position on the screen within the canvas. I need a velocity. Now, if you're just getting a unit velocity, that's a unit vector. That's a unit direction. That's a direction you're heading. So right here, I'm going to get a unit vector for my velocity, and that's a value between -1 and 1 for the x and y arguments of this vector. To do that in p5.js, it has a method called random2d, and it will return, it'll basically do this create vector, but instead of having 0 to width, it'll have -1 and 1 for the randomness of the x argument, and it'll have -1 and 1 for the randomness of the y argument. It's a lot easier to just type this than it is to type all this. I mean, here, I'll type it out, what it's actually doing here, and you guys can see the difference. These two lines do the same thing. They do the same exact thing, except for it's a lot easier to type out p5.vector.random2d than it is to type create vector quantity random quantity -1. It's just ridiculous. So instead of doing all that, it's a lot easier to just use the method that's available. And this method, since it's like enveloped into the p5 and processing in Java library, will probably run faster than if you have to have all of these keywords typed out and then they have to be looked up, reorganized, and that's already done when you're using this. So this might speed up your program just a little bit if you do it this way, and plus it's easier and faster, and it's probably going to be more accurate. So that's our unit direction. That's which way we're heading, and we'll go that direction at the unit speed, which is between 0 and 1, or 0 and -1. If we want to go faster then we have to multiply it, and this is where our magnitude comes in. So we're going to increase the magnitude of this movement by a random order, and that's going to make things move faster and slower across the screen, so the particles have some variety in how fast they're moving. To do that, we want to use the variable, this dot velocity, and then we're going to use the method dot multiply that performs some vector math and multiplies those x and y arguments relationally. You can't just add whatever to x and add whatever to y and expect it to work unless you do the vector calculations, and then it will work. p5.js will do that for you. You just have to use this proper syntax. So you would use dot multiply, dot add, dot subtract. All those operators will perform vector style math on these xy coordinates. So this vector, whatever -1 to 1 value for the x and y that's returned here, it's going to get multiplied times a number between 0 and 3, and then we're going to add to that 1. So at least we have, if the number is so close to 0, it might as well be 0, then when we add the 1, it at least takes it up to a unit movement, to 1 unit movement. And then the possibility of it being up to 3 units, or 4 units, 3 units more, so a total of almost 4 unit movement, or 4 times magnitude, 4 order magnitude. We want the particles to sway back and forth with Perlin noise, so it has this kind of organic relational feel to it. So like it's moving in a draft of air or a volume of gas. So we need a variable for that, and I'm going to use n offset for noise offset. And we want to start out with a random value so that all of the particles have their own unique set of noise values. Our stroke weight is controlling the size of the particle or the scale of the particle because I'm drawing it as a point, and a point's size is defined by its stroke weight, not its radius or diameter or width height dimensions. There's no dimensions for a point, it's just the stroke width. So I want that stroke weight to be a random number between 25 and 125. That's going to give me a variety in our scale of particles. I want this particle to glint every once in a while to kind of increase in its brightness and then fade back down. And I need a variable to hold that amount, that whatever value I'm going to put into the appearance is going to be held by glint. And it's starting out as 5. So the base appearance value, I think in this case it's the alpha for the stroke, is 5, and maybe added to some other value. That's going to go up, getting brighter and then fading back down. To do that movement up and down, I have a variable called Gpool. It starts out as 0, so there's no movement. This is holding the movement, whether it's a negative number or a positive number. And I had this idea where I just multiply it times a negative number to get it to move up and down these values. But I run into a problem with that because of the randomness of how it glints. There's a solution to it, but I didn't implement it. I figured it was just easier to do it this way than to try to implement the solution and test that because it wasn't really working. I was like, okay, I'm wasting all my time testing this other way. I know this way will work. I'll just do it this way. And it did work. So I'm going up and down by this value here, and it starts out as 0, so there's no movement. So if they're not glinting, they're just at their faintest alpha. But then if they're glinting, this is given a value that's going to move it upward, and then once it reaches a certain brightness threshold, that value gets changed and starts falling down until it gets down to its base, and then it just holds there. So that's how these variables are functioning in this update. I need a rate for that movement, the fading up and fading down. I want it to happen at a variable rate. So I need a variable to hold its initial rate, which is 0.05. And then I can make them glint quickly or glint slowly. So maybe they're rotating quickly and you get a fast glint, and maybe they're rotating slowly and you get a slower glint. So once I have all my initial variables, I'm ready to do my method that does all the business. I'm going to name that function update, this.update. Inside that, I need to increment through my noise offset. So I'm going to take that this.n off, and I'm going to add to it a small number so to increment slowly. I don't want them to fly back and forth, vibrating back and forth. I want them to kind of sway. I want to move their position to the next location dependent of its velocity. And I do that by adding to the position vector the this.velocity vector. So I'm adding those two vectors together using the add method for vectors. Once I've moved it, I need to check to make sure that it's not out of bounds, and if it is, I need to handle that. To do that, I'm just going to call a method inside update. That method is going to be down here. I'll just do it now. and I need to be consistent. I want to call it bounds with an S. So down here is going to be a function that holds some conditions that will constrain where this object is located on the canvas or around the canvas. So once I have everything checked out and I have good positional values in that, I'm going to assign a local variable called X. This is going to adjust the actual X position and make it sway back and forth. I want to do that by mapping the noise. So I'm going to find an interpolation of the noise offset return, which is a value between 0 and 1. I want to interpolate that to a bounds that is the width divided by 2 negative and the width divided by 2 positive. So I have the half of this, it can move half of the screen to the left or half the screen width to the right. And it doesn't matter where it's at on the screen. That's just the size that I'm bounding it to. So a lot of times when this is animating, there will be several particles that are off the canvas. They're floating out in the edge. And I wanted it that way because I didn't want you to see where it was coming off of one edge and going on to the other in case it has to wrap around. Then that blows the whole effect. I wanted it to look like a new dust particle was coming in on one side as another one went off the other. And then that kind of ties the volume together. It makes the particles look like they're all inside the same volume of gas. Once we have our X position, now we have to do this thing where we create our blurring. So if we just drew a point, it would be a solid color from one edge to the center. It would be kind of like the same intensity of brightness. I want that to be graduated. So I want there to be a gradient from the center to the edge. I want the brightness to fall off into nothing. So I get this kind of blur effect. To do that, I'm going to create this stroke, this point, in a loop. And I'm going to start out with a small point and make a bigger point. To do that, I'm going to create a loop. I'm going to call it D for diameter. And it's going to start out at its full size, which is that stroke weight. And then if it gets below a certain diameter, 15, it's going to stop, it's going to be done making the particle. So I want to decrement D by 10. And you can change this and it's going to change the characteristics of the particle. It's going to make it more dense or less dense. If this number is bigger, you're going to see the concentricity more. If it's smaller, then it's going to be more dense and less obvious how the particle size diminishes to create the particle. Our stroke weight is the scale of our particle. So we're going to put that, its maximum size, whatever that initial value is, and then we're going to subtract from it the value of this loop. So the particle is being drawn in the center, in its center diameter, really small. Then it gets marginally bigger, it's drawn again, gets bigger, drawn again, gets bigger, drawn again, until you get the full-size particle. Our glint is kind of the weird thing. Like I said, it's going to set at a resting state until it's triggered, and then it's going to move. And I have to increment it whether it's moving or not. So right now, this value is 0. So even though this is set to increment, it's incrementing by 0, so it's not really doing anything. Once glint is triggered, this is given a value, and then it starts incrementing. Once it reaches a certain point, then it's given a negative value, and even though it's incrementing here, it's incrementing a negative value, which means it's subtracting, it's decrementing. So I want to test to see, should we be glinting? I want there to be a random chance that it will glint, and this will be looks like 1% chance, or 1/10 of 1% chance, somewhere and around there. So I want that rate to move a random amount whenever this condition is triggered. So if we are glinting, I'm going to set the glint rate. I also need to set the polarity, the movement, to a positive number, which is that rate. Now we're going up and then the particle is getting brighter. So if the particle gets too bright, I need to check for that. How bright do I want this particle to get? 20 is about as bright as I want it to get. That's where it's just noticeable. I don't want it to be too much, because then it looks like a light flashing. And I want it to look like it's reflecting and not flashing. I don't know, it's just kind of weird. You guys can play around with that and see what works best for you. So if it's past that amount, I'm going to make it equal that amount. And then I'm going to change the movement of that increment or decrement to its negative. So now it's going down. And if it goes down too far, then I want it to stop. And I'm going to set that at 5. So if it gets down to below 5, I'm going to set it to 5. And I'm going to shut off that increment or decrement value by setting it equal to 0. So that's how glinting works in this program. That's the algorithms for glinting. So once I have my glinting, which is the alpha of the stroke, I can put that in there. And then I want it to flicker. So I can add a random amount of glint. In this case, I want to add a random amount of half the glint. Kind of kick it up a little bit so it looks like it's flickering using the glint value. Once I have my stroke weight, or my particle scale, and its stroke, or its appearance, how bright it is, then I can put in the point, use the x argument for our this.pause vector, and I want to add to it the local variable x. This is going to make it move, it's going to make it sway back and forth. Then I'm going to take the y argument from our this.pause vector and put that in there for the y argument of our point. And then that's all of that. So that's all of the update part of the function, I think. So now we just have to do the bounds method that's in this function. And that's pretty easy. There is a little bit to it though. I wanted to extend the bounds. So I want the canvas width and height to have an extra edge that we don't see. And that way particles can move off out of our view, and then if they go to the other side of the screen, they're going to come on out of our view, and things aren't going to match up perfectly, so that it ends up looking like a new particle. It doesn't look like Pac-Man went from one side of the screen to the other. So how we do that is we're going to assign some local variables inside that method. That's going to be a percentage of the width, in this case 1/2. We're going to do that for the x and the y, and I'm calling it extend x and extend y. So extx, exty extends the boundaries. Then in our argument, our condition, we can put a test for that extended x. So now this is less than 0 by half of the screen. That's our left edge. So if it's past the left edge, I'm going to need to set it to the right edge. And that's going to be the width plus that extended value, that extender. And we're going to repeat this for the y. Just going to change those last x's to y's and change the width here to height. We need to do it for if it's past the right edge. So just switch those variables around now. I think that's all of our checks for the bounds. All right, if we cross our fingers with any luck, this program should run. So I'm going to press play and see what happens. If you got this output, congratulations. You typed this program in correctly, or you downloaded it from the link in the description, and now you're playing with it and having a wonderful time trying to get these orbs to do all kinds of crazy things. Let me roll through this code just one more time slowly in case you didn't get this output and you're not sure where you went wrong. Here we go. You can check it line for line. That pretty simple program, super cool effect. You could add a picture to the background and then have these dust motes floating over the top of it to give it some kind of lifelike effect. You could add it to your animation. All kinds of things you can do with this little bit of program here. Hope you've enjoyed this program. If you have, leave a like. Subscribe if you haven't. Hit the bell if you want to see more. And I guess until next time, as always, take care.